Okay, so I got a question from the client text, and the question is apply the skill. Where am I here? Oops. Apply the skill 13.6. And I don't have, oops, wait a second here. Okay, apply the skill 13.6. And I wanted to bring this up after I got the video started, but I don't have enough windows to do that. So 13.6. So I want to go back and remind you, it's a very important thing. This comes from chapter 3 in Klein, but every organic text has got this same concept in it, and it is that an acid and a conjugate base are going to help us predict about pKas and how strong an acid is. So specifically, let me remind you, this whole thing is the acid. You know what? The whole thing is an acid. Okay, that's the acid right there. The conjugate base, I want to get rid of that. Get rid of that right there. The conjugate base of this acid is here. That's the conjugate base, and this is the acid. There's the ionizable hydrogen, which I'm going to call a proton, and this is the ionized hydrogen, which I'm oftentimes going to simply call a proton, because a hydrogen with no electrons is just a proton. So, all right. So we need that, and I'm going to refer to that in class, and every time we talk about this, I'm probably going to draw this up on the board, and I'm going to say, don't forget that in order for us to evaluate the strength of an acid, we have to look at that, the stability of the conjugate base. That is the big deal. Sunshine. That is the big deal. So every time we are considering the strength of an acid, we're going to take a proton off and look at the stability of the conjugate base. So that said, let me go back here to black, and let's look at this and say that the more stable the blank, the stronger or weaker the acid. You know what? Pause the video. Pause the video and look at chapter 3, or guess, or something, but don't let me just read this to you. Pause it and fill in the blank and circle stronger or weaker. Okay, I'm going to assume that you obeyed me and that you paused the video because you are a team player. So the more stable the conjugate base. Now, if you didn't pause the video the first time, pause it now and circle stronger or weaker. The more stable the conjugate base, the stronger or weaker the acid. Okay, I'm going to assume you paused it and you're back with us, and it turns out that the more stable the conjugate base, the more likely it is the reaction is to go in this direction, right? If it's more stable, it's going to go that way better, which means that this is a better acid. It's a stronger acid. All right, this is a big deal. We are always going to be looking at the conjugate base, evaluating its stability, and predicting pKas thereby. So remember, lower pKa equals a better acid, or stronger. Okay? Maybe it would require a different video for me to remind you about why that is the case. But this is sort of the conclusion. We have pKa tables, we memorize pKas. It's very powerful for us. Okay, that said, let's go to question 13.6, which looks like this. The question is, consider the structures of 2-nitrophenol, just right here, 2-nitrophenol, wait, 2-nitrophenol and 3-nitrophenol. Consider these two structures and say why their pKas are different. So first of all, in order to evaluate their pKas, we find an ionizable hydrogen, which is here, and these other hydrogens are simply not going to come off of there. Right? There's other hydrogens on here. They're not going anywhere. This is the ionizable hydrogen. Somebody's going to wonder why I didn't put hydrogens here too. Turns out they're there, but we don't care about them because this is the ionizable hydrogen. We strip that guy off and we'll look at the conjugate base. Conjugate base. Sure how to spell conjugate there. Okay, now we say to ourselves, are these of equal stability? Well, it turns out that they both exhibit resonance within the aromatic ring. But there's a resonance structure which is possible here that this guy down here doesn't have it. I'm going to show it to you. This guy goes here. This guy goes here. And this guy goes here. These lone pairs of electrons this is resonance now, so I'm going to draw it with a special arrow. You know what? Get rid of that. So I can go back to black. Messy here. My video, so I can take my time. Minus. Minus. And plus, because actually it still has 4 bonds. So here's an additional resonance structure. Let's see if we can do the same thing. So this, you know what, oftentimes when we're doing resonance, I'm going to put brackets around it. There's more. These are not the only resonance structures of the conjugate base of 2-nitrophenol. There are more, and they have to do with the electrons moving around in here. But for now, let's consider that one. Now let's come over here and see if we can do the same thing over here. And if this guy goes here, this guy can go here, and these electrons simply we can't get these electrons up in the system. Okay, so they're not going to go up into the nitro. Cannot go up into nitro group. Okay. Let's try another way. Let's go the other way. Say they come here, which I guess those 2 arrows are the same, right? But there's no electrons here. They can't move, right? I can't move these over here. Because if I were to do that, then I would have missing electrons right here. There'd be a plus here. And it's simply not going to happen. So they can't go here either. Cannot go up into nitro group. Okay? All right, so that's the answer. But I want to give you an additional question now that you've asked. It's a good question. Someone asked me, hey, these resonance structures look the same to me. I want to leave a question for you, which I'm not going to answer now. I'll answer on request. And that is, how willing is this nitro group to take up the extra electrons, and why? How able, let me say able and willing, is nitro group to take the extra electrons as they are here? Okay, do you see how I got the extra electrons up into here? Here, the overall formal charge of this whole group is -1. Normally, the overall formal charge is 0. Right here, it's -1. And here is 0. As in all resonance structures, we have the same number of electrons. So you see how this nitro group took the extra electrons. That's what I'm talking about. How able would it be that? Okay? Is that a good thing or a bad thing? Is this nitro group likely to take those extra electrons? Is it capable? We see it's capable because we draw these up here. But how able is it? How much stability does it confer? And I'm not going to answer that right now. I'll answer that in a request. So hopefully this is helpful. Appreciate the questions from the class via email and texting. I encourage you to keep them coming.